Okay, we went through the scenario evolutions for the pre-RCPs, so up to SRES and then into RCPs, which were used in the assessment report 5, and assessment report 6 has been released, which used the so-called shared socioeconomic pathways. So we'll look at a review of this particular transition from RCPs to SSPs and look at some of the results, the methodologies, and maybe a little bit of a caveat along the way. The shared socioeconomic pathways and their energy, land use, and greenhouse gas emissions implications and overview. So this is not just an evolution, but what are the implications of these assumptions that are made in developing these scenarios. The paper presents the overview of shared socioeconomic pathways and their energy, land use, and emissions implications. The SSPs are part of a new scenario framework established by the climate change research community in order to facilitate the integrated analysis of future climate impacts, vulnerabilities, adaptation, and mitigation. The pathways were developed over the last years as a joint community effort and describe plausible major global developments that together would lead in the future to different challenges for mitigation and adaptation to climate change. So you can see how things have evolved over time. Adaptation was almost a taboo word in the beginning because it was assumed that saying we can adapt to climate change would basically somehow lead to the assumption that we can adjust to climate change so we don't have to mitigate climate change. So mitigation was a bigger focus, but now it's more than obvious that even as mitigation keeps on happening, let's say in terms of implementation of renewable energies or EVs, transportations, changes and so on, we will still need adaptations to manage the unavoidable. You know, the old cliche is that mitigation may be to manage the avoidables, and adaptation is to manage the unavoidables, or avoid the manageable, unmanageable, and manage the unavoidable. Whatever. Those kinds of words are fancy, but in reality, the SSPs are based on 5 narratives describing alternative socioeconomic developments, including sustainable development, regional rivalry, inequality, fossil-fueled development, and middle-of-the-road development. So now we have gone from science into fully engaging the socioeconomic, socio-political scenarios, because regional development is one thing, but regional rivalry is geopolitics, so you are creating scenarios. Do they all work out? Well, if you look at Russian invasion of Ukraine, which is my favorite example, or COVID, for example, for that matter, then you see that it's not so easy to think of what may happen in the future. The long-term demographic and economic projections of SSPs depict a wide uncertainty range consistent with the scenario literature. A multi-model approach was used for the elaboration of the energy, land use, and emissions trajectories of SSP-based scenarios. The baseline scenarios lead to global energy consumption of 400 to 1200 exajoules in 2100. That's quite a large range, 3 times from the lowest to the highest, and feature vastly different land use dynamics, ranging from a possible reduction in cropland area up to a massive expansion of by more than 700 million hectares by 2100. Of course, implicit in this is food demand, bioenergy demand, and population growth, which we will look at. So those are not always easy. The other thing that one should be careful, maybe we'll return to this somewhere else, that even as you are plotting the future pathways and emissions, concentrations, temperature evolution, and impacts into precipitation and other things, the climate change response itself is not constant. So there is this thing called climate sensitivity, often also referred to as equilibrium climate sensitivity, which has certain definitions. I have podcasts on climate sensitivity, equilibrium climate sensitivity. This concept is complicated, and it's not even clear what we would do with equilibrium sensitivity, because that means we have stopped emissions and just waiting for the climate system to equilibrate. When will that happen? Well, not anytime soon. But there is a transient climate sensitivity, which means how is climate responding as emissions are still changing, which is the situation for the 21st century. And for models, this is a very complicated issue, because models don't all produce the same sensitivity to the emissions. So we'll come back to that later in terms of cumulative carbon and how that tends to linearly relate to warming, global warming. But then you don't know about the non-CO2 greenhouse gases. So this is a complicated business about how climate will respond to emissions and these land use and energy and so on into the future. The way projections are dealt with in or the way these uncertainties are dealt with in the projections is to put these plumes or probabilities around the value for each scenario. So if temperature is going in one direction, you have a probability around it, 33% to 66% and so on, which is presumably taking care of these uncertainties of the evolution of climate response along the way. The associated annual CO2 emissions of the baseline scenarios range from about 25 gigatons CO2, more than 120 gigatons CO2 per year by 2100. So you can see that's a huge range as well, more than 4 times, almost 5 times. With respect to mitigation, we find that associated costs strongly depend on 3 factors: policy assumptions, socioeconomic narrative, and the stringency of the target. This is where a lot of the debate comes in, because integrated assessment models are used to do these things, socioeconomic narratives and meeting the target with various options like bioenergy, carbon capture and sequestration. But are these models even capable of doing this correctly? This is a big debate that I'll get into a little bit later on. Okay, the carbon price for reaching the target of 2.6 watts per meter squared that is consistent with a temperature change of limit of 2 degrees C above the pre-industrial level with some probability like 66% differs in our analysis, thus by about a factor of 3 across SSP marker scenarios. Again, marker scenarios are the draft versions that were put out. So now we are combining RCPs with SSPs. So RCPs talked about 2.6 watts per meter squared in terms of energy imbalance by 2100 above the at the top of the atmosphere. So additional forcing created by human activities, fossil fuels, etc. So we had 2.6, 4.5, 6, 8.5 and so on. And now we are associating a global warming target with those. Okay. Moreover, many models could not reach this target from the SSPs with high mitigation challenges. While the SSPs were designed to represent different mitigation and adaptation challenges, the resulting narratives and quantifications span a wide range of different futures broadly representative of the current literature. So this is again like RCPs, depending on published literature and a community to develop them separately from the people who actually do the simulations and projections for the future with the Earth system models. Okay. This allows their subsequent use and development in new assessments and research projects. Critical next steps for the community scenario process will, among others, involve regional and sectoral extensions, further elaboration of the adaptation and impacts dimension, as well as employing the SSP scenarios with the new generation of Earth system models as part of the 6th climate model intercomparison project. So this was published before CMIP 6 was released, and we already have CMIP 6, and I have summarized CMIP 6 in detail and with the final version released in 2023, so you can look at those. But here again, the question of whether models that are unable to meet the 2.6, sorry, under 2 degree C goals, what does it mean? Are the models that are actually meeting it being realistic, or are they tweaking the models to go in directions that the models actually are not capable, like the scale of the mitigation or the time scale of the time scale over which the mitigation happens. So there are all sorts of criticisms of how this was done. The main one being that these goals, 2 degree C and then 1.5 degree C, were not bottom-up science-derived targets. Okay, we'll talk about that elsewhere, but these were handed in different ways, and then impacts and science were being retrofitted, are still being retrofitted. The question is whether the models are even capable of saying exactly what will happen if we cross 2 degree C or cross it for a period and come back, and so on. So many details are involved. If this podcast gets too long, I'll split it into two, but let's keep going. Schematic illustration of main steps in developing the SSPs, including the narratives, socioeconomic scenario drivers, so the basic SSP elements, and SSP baseline and mitigation scenarios. So arrows going in all directions, so there is no loop, so we can just start somewhere. So there is, let's say, narratives or the storylines, which are these development pathways, regional rivalries, sustainabilities, and so on. Along with those come the challenges in adaptation and challenges in mitigation. So we will see that phase space and how it plays out. So the SSP scenario drivers are things like population, urbanization, and GDPs. So GDPs still have the Kaya identity in them in terms of the energy intensity of the GDP and carbon intensity of the energy, which affects, of course, the emissions. And just as we are talking now in June of 2023, last year the emissions from energy production reached a new record. So we have to always keep tracking these. So the SSP scenario drivers also go into the SSP web database, which is served here. I'll just read these before going here. So they include country projections, so GDP, POP, education, and urbanization. Let me stop. My floor needs to be mopped here, so I have to stop this for a sec. Okay, sorry about that. This happens when you work from home. So there was a demand to make the projections for the future more regional. Elsewhere I have talked about the problems of trying to do this, because if you think about Earth system models, they are very good at, let's say, simulating temperature compared to precipitation. But even in temperature, the reliability of the models is good at regional scale. So it's not at let's say a subdivision of India, but it at the subcontinental India scale, and precipitation is much more problematic. So what are the uncertainties when we take these models and try to produce country level projections in population projections are always problematic, as we will see. So the integrated assessment model outputs for 5 regions are given here: energy supply and demand, land use and land cover change, greenhouse gas emissions, air pollution and aerosol emissions, mitigation costs, and prices, etc. So each one is kind of a storyline. Integrated assessment models themselves are debated as whether they are good enough or up to snuff on doing all these things and so on, which I have discussed elsewhere as well. You can follow up, but here we will just look at how SSPs evolved and how closely they have relied on IAMs. Sometimes IAMs are integrated or iterated with ESMs, because if you develop scenarios from integrated assessment models and give it to Earth system models, then you should remember that Earth system models produce changes in carbon cycle, nitrogen, other greenhouse gases, which affect the evolution of temperature, and that has to essentially feed back to integrated assessment models, which assume temperature dependence of various things like agriculture, GDPs and so on. So this is a complicated business as well. But nonetheless, you can see there is information being fed into the database, but also SSP scenarios are going into baseline scenarios and mitigation scenarios, and narratives also feed into that. And each one has a reference associated with them, so you have to see how the SSP development happened with existing literature as well. Baseline scenarios done with 6 IAMs, 5 marker scenarios, 19 non-marker scenarios depicting uncertainties. Mitigation scenarios, shared policy assumptions go into that. 4 long-term radiative forcing targets, so RCPs are feeding into SSPs. 81 mitigation scenarios, assessment of costs and feasibilities are included as well. And here are the models that participated in them, the 6 IAMs. Why do we have 6 models? Because each one has a slightly different assumption, slightly different framework, and different scales in space and time, different assumptions, different damage functions, different ways in which they translate climate forcing into various socioeconomic things, and so on. So what is the point of having so many models? Well, it's like having many car models as well. Some are cheaper, some are more expensive, more focused on luxury, some are race cars focused on performance. So this is how you can think of it if it helps you. But nonetheless, you cannot have one model which is perfect for everything, so you end up having multiple models. And modelers in general are just intellectually curious, so they like to develop their own models as well. Okay, and reality check has to happen to all of them in some ways, but with IAMs you are just providing scenarios, narratives, storylines. How do you validate them? That's not always it's not as easy as ESMs. ESMs give you temperature, precipitation, humidity, which you can check for historic periods and make sure they are working well enough before going into the future. Development of the SSPs comprised 5 main steps as illustrated in figure 1, which is this. Design of the narratives providing the fundamental underlying logic for each SSP, focusing also on those elements of socioeconomic change that often cannot be covered by formal models. Extensions of narratives in terms of model input tables describing in qualitative terms the main SSP characteristics and scenario assumptions, which you can look up in the supplementary material of this paper. Elaboration of the basic elements of the SSPs in terms of demographic and economic drivers using quantitative models. So we are talking about qualitative and quantitative and mixing and matching, which then spits out something. So you have to take that with uncertainty estimates, which came here from the 19 non-marker scenarios, for example. Okay, where was I? Elaboration of developments in the energy system, land use and greenhouse gas and air pollutant emissions of the SSP baseline. So everything is compared to a baseline, so it's a relative. So often it is like if we do nothing in terms of adaptation and mitigation, where we will end up in terms of emissions and warming, and then going below that, how do each scenario bring us closer to the targets, whether it's temperature target or mitigation and adaptation goals, right? Well, I'm just losing track here. Okay, elaboration of these elements by IAMs for the SSP mitigation scenarios. These are the steps. Let's look at this table, and maybe I should stop this podcast after that. IAM models are used for the development of SSP scenarios. For further details, you can look up the supplementary material again. Model name, hosting institution, will that help you? You can look at it. GCAM, PNNL was being run also by PNNL subsidiary or a lab of the DOE in Maryland called Joint Global Change Research Institute, for example. And There are others from NIES, PBL, EASA, this is Potsdam, theme, so I can't even tell you what all these acronyms are. You have to look them up. We haven't said what SSPs are, but we'll come back to that in a minute. So you can see the SSP marker scenarios, SSP 3, 4, 1, 2, 5. So why are different models running different scenarios? That comes to, again, what their abilities are and what they could accomplish and they couldn't accomplish. So SSP coverage in terms of number of scenarios, this was the marker scenario, but these are the all the scenarios. So they ran 22 scenarios here, 20, 13, 13, 14 and 23 respectively for each model, and then they are mixed to produce some kind of an ensemble of projections. Model category here, it's a general, I won't go into the details, you have to go and see what that exactly means. This is general equilibrium model, this is partial equilibrium, this is a hybrid, so systems dynamic model and general equilibrium for agriculture. Just remember that these are not exactly the same. This is why we have multiple models, as I said before. This is hybrid with systems engineering, partial equilibrium models linked to aggregated general equilibrium. Quite complicated. Both of these are general equilibrium models. Solution algorithm, recursive dynamic for all these. Intertemporal optimization here, intertemporal optimization for all these as well. If you don't understand what they mean, just don't worry about it. My main point here is to tell you how complicated this business is. Oops, yeah, here. So let me come back and look at the summary of the SSP narratives following the table. Maybe I should have done this before, but it doesn't matter. Here we were mostly looking at the models and what scenarios they did. And here we will look at what those scenarios actually are in terms of the narratives. Okay, so let me do that in the next podcast, since this has already gotten to almost 25 minutes. Okay, see you in the next podcast.